Welcome to this video lecture on muscle biophysics and biomechanics, presented to you today by Zack Muscle, a member of Group 4A. Today's learning objectives will cover how we measure contractile forces, and within that, how to differentiate between both isometric and isotonic contraction. And we'll also take a look at how isometric contraction relates to muscle function. We'll also look to see how muscle length and muscle load affects muscle performance in regards to strength and velocity. And lastly, we'll take a short look at the biomechanical muscle arrangement in the body and how the body uses levers to manipulate movement. We know that all muscles generate a contractile force. This force is known as the muscle tension. Tension, just like the tension in a rope or string, is uniform throughout the length of the muscle. Now we can measure tension using two methods, isometric and isotonic. Isometric means the same distance. In other words, the muscle does not shorten or contract during the muscle tension. Isotonic means the same tone, where this time the muscle shortens under a constant weight. And when we measure isometric contraction, we must be aware that the total tension that's measured actually has components of both active and passive tension. In active tension, as we've seen in previous instructional videos, the tension is generated by the actin-myosin cross-bridge cycles. This occurs during active muscle stimulation. Passive tension, on the other hand, is the tension generated by the muscle fibers when the muscle is not in active stimulation. Now that we already know how active tension is generated by the actin-myosin cross-bridge cycles, let's take a closer look at how passive tension is generated. In muscle, passive tension is the product of elastic components. These components include connective tissues, tendons which attach the muscle to bone, the sarcolemma which covers the muscle fibers, and titin, which is shown here in this magnified view of a sarcomere. Now titin serves two purposes. One, it helps maintain the integrity of the sarcomere, and it also helps to maintain the alignment between the thick and thin filaments. Now one may ask, what is the benefit of doing an isometric analysis of muscle? Well, it becomes very useful when comparing the functions of various muscles. For example, this graph shown up here on the left is an isometric twitch duration analysis graph. It shows the twitch duration of three muscles in the human body. What's interesting is that the twitch duration of, for example, the ocular muscles of the eye is very short and corresponds with its function, which is to allow rapid and precise movement of the eyes. Whereas the soleus muscle, which is in the calf, doesn't have as quick of an isometric twitch duration, which corresponds to its function to help maintain balance of the body. Okay, so what Sanita and I are about to demonstrate for you right here is isometric contraction. So we're about to do an arm wrestling competition. So let's begin. A little effort. So what you see here is that we're both struggling, we're both using a lot of energy, but there's no movement. So we call this isometric because it's the same position. Now this is going to remain isometric until somebody wins. Now let's talk about isotonic contraction. We know from previous slides that isotonic contraction means same tone. In other words, the muscle does shorten under constant load. Several examples include lifting a dumbbell or a weight, or by pushing a book or a chair across the floor or a table. So what I'm about to demonstrate now is isotonic contraction. So by pushing this block of paper across the table, you can see that my muscles, my triceps, are contracting, once again, but yet the load is not changing. So muscle contraction with unchanging load. Thank you. Now let's ask, now how does length affect the muscle's tension? Well, let's keep in mind that the active tension generated by a muscle is directly proportional to the number of available cross bridges. In other words, the available cross bridges are the mechanisms that generate the muscle tension. We know that deviations from the optimal resting length of a muscle reduces the muscle's active tension. So let's take a look at exactly what's happening when we change the length of a muscle that affects its tension. Well, if we take a look at this graph on the upper right-hand corner here, we'll see a diagram of a sarcomere represented at 4 different lengths. We know the average length of a sarcomere in a human is approximately 2 micrometers. This can be illustrated in either diagrams B or C. If we begin to stretch the muscle or lengthen the muscle, the sarcomere will also lengthen. This is illustrated in the diagram D. What you can see is as the sarcomeres lengthen, the actin-myosin cross-bridge heads begin to go out of reach. Some of the inner heads of myosin cannot reach the actin filament. This reduces the overall number of actin-myosin cross-bridges, which reduces the active tension magnitude. Now, when the muscle is reduced in length, this can be shown here in figure A. What happens is the myosin, or the thick filament, begins to butt up against the Z-disc line. We also see that the actin filaments begin to overlap each other. This once again reduces the total number of actin-myosin cross-bridge heads. Now, this principle, even though it is viewed in the model of the skeletal muscle sarcomere, it also holds true for both cardiac and most smooth muscle fibers. Now, this is true as long as the direction of the actin-myosin myosin heads is similar to what's shown here. Now, some of the exceptions are in certain smooth muscles where the direction of the myosin head in one direction is going in the opposite direction on the other side of the thick filament. Now, the advantage there is that the smooth muscle, for example, smooth muscle in the bladder, allows the muscle to maintain constant tension under varying degrees of volume. Now let's take a look at how load affects the muscle's contraction velocity. Now, we know that increasing the load decreases the muscle contraction velocity. Now, you may be saying, but Zach, isn't that common sense? Well, you might be right. But there's actually 2 factors at play here. The first factor is inertia. The second factor is the availability of the number of cross bridges. Now, we know the inertial factor based on Newton's second law of motion, which is force equals mass times acceleration. So obviously, for any given tension, which is the force, the load, which is the mass, is inversely proportional to acceleration, where acceleration is related to the contractile velocity. So if we increase the load, or the mass, we're going to decrease proportionally the acceleration, which affects the contract velocity. Now, the second factor that's encountered is the cross-bridge availability. Now, with the heavier load, a greater number of cross bridges are actually already active in order to maintain that target load. Now, this leaves fewer unused cross bridges to provide the additional active tension. Hence, going back to the topic, active tension is generated by the number of available cross bridges. Now let's take a brief look at muscle biomechanics. We know that the human body arranges many muscles in an antagonistic form. In other words, the muscles oppose each other in various directions. Some examples include the biceps and triceps, your flexors and extensors, your quadriceps and hamstrings, among a list of many. We also know that the body utilizes muscles and bones and complex lever systems in order to increase mechanical advantage, provide body stability, and also to increase the range of motion. Now here we see two separate antagonistic systems. First system shown here are the biceps brachii, which are antagonized by the triceps brachii. Now these two groups of muscles, or these two muscles, work against each other in the arm to provide a variety of motions. Now there are actually three classes of levers used by the body. There's the first class lever, second class lever, and third class lever. Now which of these levers do you think is the most commonly used form of biomechanical lever in the body? If you answered third class lever, you would be correct. Now what's interesting about biomechanical levers is that the tension that's generated by the muscles aren't actually used directly. In fact, they're converted to torque, which allows the lever body, or lever arm, in this case the forearm, to pivot about its fulcrum, in this case the elbow. Now because of this, the lever arm is able to exhibit a wide range or far range of motion. However, this also reduces or limits the amount of force that's generated and extended to the load. Because of this, many muscles such as the bicep has to generate tensions up to 10 times more than the load itself in order to support the load. So you can imagine, as you're lifting that 50-pound dumbbell, doing a bicep curl, your bicep actually has to generate 500 pounds of force in order to lift the load. So let's quickly go over the summary of this video lecture. We know that muscle generates tension. We know that muscle tension can be measured either isometrically or isotonically. Isometric being the same distance, isotonic being the same tone. We know that tension duration is related to muscle function. We also remember that active tension is directly proportional to the number of available cross bridges. We also know that active tension is at its maximum during the normal resting length, and deviations from the normal decreases active tension. We also understand that by increasing the load, we get a smaller contraction velocity, which is comprised of two different factors. We also know that skeletal muscles in the body are arranged in opposing or antagonistic forms. We also know that the skeletal muscles in the body use various lever systems. More specifically, most of them use the Class 3 type lever. Now, we'd like to thank you for watching our video. Please refer to our self-assessment guides to assess your knowledge on some of the major topics pointed out in the video. Any additional information, of course, can be found in Guyton's book of medical physiology, or you can contact any one of the group members in Group 4A. Thank you very much.